Hey ChemStars, this is Mrs. Vanderlei bringing you the fourth video for Chapter 4, Section 1. And we left off on this page where Planck came up with this revolutionary thought where energy is related to frequency. All right, that's huge. And his buddies actually calculated the constant of Planck's constant, 6.626 times 10 to the negative 34th. So what we did is that we calculated the wavelength and the frequency, excuse me, the frequency and the energy of the helium line of 668. So the first thing is we converted the nanometers to meters. Remember that a nano is 10 to the negative 9. And then we use that to calculate frequency. Hey, what's new? C over lambda, you're right. So we use the C divided by our lambda, which was in the terms of meters, and we got our frequency, and now we can figure out the energy of that wavelength. So what we're going to do now is that we're going to use the 4 wavelengths from hydrogen. Here, let me show you. So remember this? We just calculated the helium. Let me scroll down a little bit more. We just calculated the helium using the wavelength of this, and we found its frequency and we found its energy. We're going to do the same thing now with the hydrogens. So if you don't already have one, please get a calculator handy, or maybe use a calculator on your phone. You're not supposed to have it in class, but you can use it at home if you would like. But you really do want a calculator. Make sure you get the same answers that we're going to get. So if you need to pause this and grab your calculator, that's great. Let's go ahead and do that, okay? And then come back to the next page. Okay, welcome back. So hopefully you have your calculators, and here are these wavelengths that we saw from the hydrogen atom on the previous page. So now we need to calculate the wavelength in meters for each of these, so we can then plug it into, hey, what's new? C over lambda. You're right. We need the lambda right here to be in meters for the units to cancel out. So what did we say nano was? -9. So I just left the number the same. I didn't put a decimal in it. If you recall, I told you on the third video that that's okay. Your calculator does not know what proper scientific notation is. So that's good, okay? Just leave it like that. You'll make fewer mistakes. So don't put a decimal in there, okay? So now what? Here's my frequency. Hey, what's new? C over lambda. So here's my new. I'm using green for, I'm using green for C, just because I hadn't used it earlier. And I'm going to use that same green for the speed of light each time. And now I'm going to use my lambda that I have over here. Do you see that? I just made this number and I put it over here. And now use your calculator, okay? So plug in 3.0 EE, or maybe EXP8, not times 10 to the 8th. You're going to get it wrong. So 3.0 E8 divided by 410 EE -9. Why don't you go ahead and go click, 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 and tell me what you get. All right, this is what I got, 7.32 times 10 to the 14th, 1 over second. Why is it 1 over second? Because your meters canceled out. So the only thing left was a second in the denominator. Well, now we're ready to do the next part. What's E equals H nu? Well, here is my E equals, all right, 6.626 times 10 to the negative 34th joule seconds times, that's X is the times button, times what? Times this, the frequency that you just figured out from the previous box there. So there it is. And then go ahead and calculate that. So if you still have your 7.32 EE14 left in your calculator, leave it there. And now just go times 6.626 EE -34. And you figure this out first, and then make sure you get the same answer I get. Okay, this is what I got, 4.85 EE -19. So that one photon has that much energy, okay? All right, let's go on. Let's do blue. So how do we do blue? Well, I have this in nanometers. What's a nanometer? 10 to the -9th. All right, again, no decimal points. So hey, what's new? C over lambda, you're right. Okay, so here's new, and I'm going to put C over lambda. What's my lambda? This is my lambda, 434 times 10 to the negative ninth. There's my lambda. And what do you get? Go ahead and plug that in. Is that what you got? That's what I got. Hopefully you did that too. So now what am I trying to do? I'm trying to find the energy of that one photon. So E equals 6.626 times 10 to the negative 34 times what? Times that number, times the number you just figured out. Excuse me. The one that you figured out from your frequency, all right? And I got this. Multiply those two together and tell me what you get. So go ahead and plug these numbers in and see if you got what I got. This is what I got. Hopefully you did too. All right, what about our teal? All right, let me scroll down just a little bit. There we go. So my teal color has a wavelength of 486. So how many nanometers is that going to be? Well, 486 times 10 to the negative ninth nanometers. So now what am I supposed to do? Hey, what's new? C over lambda. You're right. So here's my C. Here's my lambda. And now let me scroll down a little more. Sorry about that. All right. So now what do I get? Well, you go ahead and punch it out and see how you do. All right, this is what I got, 6.17 times 10 to the 14th 1/2. And now it's time to figure out energy. Energy equals h nu. So here's my E, here's my H. Well, what's my nu? My nu was that 6.17 times 10 to the 14th. And now what do? I multiply those two together and I get this. So why don't you do red the entire way through, all right, and see how you do. So pause this, I mean it, pause this, do the red and come back. Okay, let's see how you do. Here we go. This is what I got. So it's 656 times 10 to the negative ninth. Hey, what's new? C over lambda. C is a constant. I put it over your lambda. Why did I need to put it in meters? So that the meters canceled out. So I got 4.57 times 10 to the 14th over seconds. And now E equals h nu. Our h is always the same number. Now I'm going to plug in my nu, and I get 3.02 times 10 to the negative 19th. Okie dokies. So why do we care about this? Okay. Why are these calculations important? Well, I'm going to tell you. All right. So what just happened? Okay. Bohr changed the idea of the atom. Remember how Rutherford came up with the solar system model, and he said that the nucleus is in the middle, and these electrons are just kind of zooming around any haphazard place, all right? No, 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 no. It's not just any old place those electrons are zooming around. They're in very specific paths that they're zooming around, and each of those paths represents energy levels, okay? What's the energy level? Those are the numbers that we just calculated, okay? So this is the Bohr model, okay? Electron orbits or energy levels. Electrons can circle the nucleus and only in specific allowed paths or orbits at certain energies, no place in between. The energy of the electron is greater when it is in an orbit further away from the nucleus. So if you look at the solar system, the ones from Jupiter are going to have more energy than ones from Mars, okay? The atom achieves ground state when the atom occupies the closest possible positions around the nucleus. In other words, Mars is going to get filled up before Venus, which is going to get filled up before Earth. Did I say Mars? I meant Mercury. Mercury is going to get filled up before Venus, which is going to get filled up before Earth, and then we're going to fill up Mars, okay? That's what that means. So the electromagnetic radiation is emitted when packets move closer to the nucleus, and those are your photons. Look at photo, think of light. So this is an energy packet with the energy equals h nu. All right, so we have energy transitions. Energies of atoms are fixed and definite quantities. We also call that quantum. Energy transitions occur in jumps of an exact amount of energy or a quantum of energy. Electrons only lose energy when they go to a lower energy state. Let's go to the next page. This graph is really important, okay? These are the energy transitions for the what? For the hydrogen atom, and that's key, all right? This works for the hydrogen atom. You notice that mine is in color. This is why I wanted you to have those colored pencils from the third unit or the third video, all right? Because these are all the different possible transitions. So if number one is the ground state for certain electrons, if I gain enough energy, it's going to go up to n equals 2, n equals 3, n equals 4, all the way up to n equals 7. So then it'd be in an excited state. Woo! All right. How does it get back down to its ground state? It has to jump. Okay. Well, which one is the biggest jump? Well, I'm looking at the Lyman series, and that has the jump from 7 to 1. That's a huge jump. It's like me jumping off a roof or something, okay? That's a huge jump. It has the most energy. Now, what really made Bohr's atom believable for all those scientists is actually the Balmer series. All right here. Notice what I've done. I've made these colorful, haven't I? Oh, I did. All right. So go back on that prior page. Okay, let's do it. So what did we notice here? The purple has an energy, go over here, of 4.85 times 10 to the negative 19th. The blue is 4.58 times 10 to the negative 19th. The teal is 4.09 times 10 to the negative 19th. And the red, let me scroll down a little bit more, was 3.02 times 10 to the negative 19th. Well, let's go back over this page again. Notice there's your purple right here. That has your longest jump. It has the most energy of those four colors. Why? Because it's going from n equals 6 to n equals 2. What about that blue, the next one? It was the next largest energy right here. This is my way to try to make a teal color. Didn't work out too well. So my teal was from n equals 4 to n equals 2. My red had the longest wavelength, but the littlest energy. It had the shortest jump. All right. So these are your colors. Do me a huge favor and use those colored pencils that you got out and mark this line as the purple line. Mark this line as the blue line. Mark this line as the teal line, and mark this line as the red line. These lines represent, there we go, these right here. Those lines represent those energies. So what do you notice, all right? As the wavelength goes up, all right, as the wavelength increases from purple to red, red has the highest wavelength, purple is the lowest, all right? What happens? Frequency goes down. Look at these numbers, 7.32, 6.91, 6.17, and energy goes down, all right? So as the wavelength goes up, as you go from purple to red, frequency goes down and energy goes down. Let's go back and look at this picture again. So red has the longest wavelength, but the shortest energy. All right. Green or teal has the next longest the next longest wavelength. But the next shortest energy. Purple had the greatest energy, but the lowest wavelength. It was like 400 and something, if you remember right. So that's great. Now, what do you notice about this line? It's kind of gray. It looks kind of like a ghost, doesn't it? All right. This line right here represents your UV light. All right, UV has higher energy but a lower wavelength, doesn't it? Okay, it does more damage. UV can cause, skin cancer. All right, visible light does not. So, what do you think? Let me think. I bet infrared might show up over here. I bet maybe microwaves show up over here. I bet X-rays and gamma rays might be over here. Remember gamma ray when we had those excited the excited atoms? Well, look how much energy this would have, all right, if it's an electron transition, okay? So anyway, these lines represent those different forms of electromagnetic radiation, okay? So let's kind of scroll down a little bit. Okay, so look, the more energy, you have a greater frequency and a smaller wavelength. This is important. Less energy has the lower frequency and a greater wavelength, okay? So which has more energy, red light or violet? Well, it's violet. Why? Because it's jumping from n equals 6 down to n equals 2. That's a much bigger jump than n equals 3 to n equals 2. So those jumps represent energy. Also, violet has the shortest wavelength, okay, that 410, greater frequency and greatest energy. If we go back to that page one more time, we will see that. So which has more energy, UV or visible? It is UV. Why? UV has the greatest jump from 7 to 2. Visible is from 6 to 2, 5 to 2, 3 to 2, 4 to 2, 3 to 2, and even IR. I thought I'd throw in IR even though it wasn't asked for. It's actually part of that Paskin series, and it goes only to n equals 3. So it's still a shorter jump, all right? And that was the huge breakthrough that allowed us to understand more about the atom and that those electrons are in exact energy levels, all right? But guess what? There's more to the story, and that will have to be the next video. So don't wait to be great. We'll see you next time. Bye-bye, everyone.